I would suggest we start. So welcome everyone to this first installment of the ICAI Mercury Machine Learning Lab webinars. So this will be a series of 4 webinars in the next few weeks. In case you don't know, the Mercury Machine Learning Lab is one of the ICAI labs in the Netherlands and is a collaboration between the University of Amsterdam, Delft University of Technology, and last but not least, Booking.com. And the lab involves different research topics, so information retrieval, natural language processing, reinforcement learning, and causality. And in these 4 webinars, we would like to address each of these 4 topics. And for today on the program, we have causality. I'm really looking forward to the presentation of our speaker for today, Juan Correa, whom I will introduce later on in more detail. Because first, I would like to give the floor to Onno Zoeter from Booking.com, who kindly agreed to give a short introduction to the lab and its mission and its purpose. So, Onno, if you're ready.
Yes, thanks, Joris, and thanks everyone for being here. We're all super happy to officially launch now the Mercury Machine Learning Lab. Maybe before I start, you might wonder why Mercury? Well, Mercury was the Roman god of very many things, but among them, the Roman god of travelers and the Roman god of science. So we thought it was a fitting name to name our collaboration after Mercury. What I'd like to do today is give you a brief motivation for the first of the 2 themes in the lab. We have natural language processing is a theme. The other theme is learning from controlled sources. And learning from controlled sources is deliberately a vague or imprecise name. And that isn't, you can take it as a sign of humbleness, is that we don't think we've yet discovered a single unifying mathematical description of the problem with a well-accepted academic name for it. And this is where information retrieval, particularly offline evaluation and offline learning, causality and reinforcement learning come together. And to give you an idea of what this challenge is about, I want to start with running you past 3 challenges. You're all smart people, so I guess you all love challenges. So you can follow along, see if you can pick out what's going on and how you'd solve it. So here's a classic, potentially classic supervised learning problem in a medical situation. So there's historical records, patient records, where there are measurements at the patient's XI, and then a simplified recovery of the patient, yes or no. So it looks like this is a classic binary classification problem. And the ambition is to learn a model P of y given x. And this is a scenario where on held out data from the historical data set, the test performance is really very good. But then in practice, when the model is deployed and it is used as a signal for doctors, then all of a sudden the predictive performance of this model gets a lot worse. And the hypothesis is what's going on is that when the model signals that the chances of recovery are low, the doctors will intervene, and they're often successful, and therefore negate the prediction of the model. Right? Second example is that of offline evaluating of a ranker using clicks. Right? So suppose that there's a big e-commerce company that hosts a Kaggle competition to invite academics and other groups to come up with a better ranker, right? And so they share click data, which consists of the context, XI, that is measured at this creation time, the actual shown lists, LI, and then the buying decisions, BI. And now the contestants are asked to submit a ranker, which should take the context and produce a ranked list of length K. And the way this competition is scored is by taking some data, holding it back, test set, sharing the context and withholding the actual buying decisions, And so submissions to the competition that have ranked these actually bought items very high get a higher score, right? And how these things are combined into a single number, you can use NDCG or MRR. The details of that is not important for this example. But in this particular case, the outcome was surprising. So the winning submission was very similar to the ranker that the company was already using. And that was surprising quite a lot of people because they knew that the existing ranker had big omissions. There were big important categories that the ranker was not serving, actually. So that's the second problem. And the third problem is that of credit card approval. This is actually a rumored old, very early attempt at using machine learning in the 80s. So this was in a time when human assessors would make a decision if customers would get a credit card, yes or no. And so given observed information, such as credit score and answers to a form in the application form, and then possibly question answering of these human assessors with the applicants, the human assessors needed to estimate the risk of default, YI. And they would accept, they would hand out credit cards only to applicants with low risk, right? So default would be not repaying your credit card loans. And that will be, of course, quite costly thing for the bank. And then the argument of the bank says, well, after a few years, they have a big data set with historical pairs of what is measured, XI, and the actual data of repayment or default on loans, right? And so they want to learn a model P of Y given X to automate this process. So to let this human assessor do other stuff. And here again, it's an example where on held out data, the predictive performance is very good. But when the model actually replaces the human assessors, the performance is a lot worse. Right? So we'd like to make a first claim is that for many real world applications of models, even just regression models, the problem is a lot richer than just supervised learning problem, than just the classic supervised learning problem that you would get in your first machine learning course or in Kaggle competitions. And so now let's revisit and think a little bit about what might be going on. So what is happening in the medical example is that the actions of the doctors are left implicit, right? And if you only test yourself on held out data from an historical data set, where both in the training phase, in the training data and in the test data, there's the same more or less stationary default policy of doctors running, that is not so much of a problem because you integrate, you take expectations out of these policies. However, after you deploy the model, just the mere fact that you deploy the model will trigger a change in this policy. Right? So what you'd actually want to do is you would want to model not just in terms of what you can measure on the patient, but also in terms of the actions of the doctor. Right? So as a function of the policy. You should then also be mindful that for new policies, because you'll be using new policies, you'll start out essentially with very little relevant data to predict what might happen. Right? So you'll need to actively learn once you've deployed the model. Second example, that of offline evaluating for ranker. Here, the obvious problem, of course, is that the position effect is a big effect that is missing. Right? So which items are bought in your test set? Well, these are the items that the old ranker ranked high. Right? And so if the ranker that the contestant proposes correctly finds this whole category of items that the old ranker might not have shown, that might be a great improvement to the ranker, but this contestant will get 0 points for that improvement, right? And therefore it will likely lose in the competition. And it means that you can reason through that you can even get stuck, even if you think, well, we will iteratively improve and let our ranker slowly get better over time. If you ignore this position effect, you can get stuck. Okay? And you might argue, say, well, position effect is such a well-known thing. How, this is unrealistic that this would ever happen. That's not the case. I've seen this mistake a few times in my career already, and this hypothetical Kaggle competition is actually a real thing. You will see, if you look at the Kaggle competitions, a big travel company, not Booking.com, that scored exactly in this way. Third example, the assessors and the credit card, what is happening there, of course, is that there's a filtering effect. So the human assessors have filtered out the most risky cases. Right? And when the model replaces these human assessors, this filtering stops. And so after seeing just these three examples as more or less as toy examples, I want to make another claim. So not only is this problem richer than just a standard supervised learning problem, there's also not yet a generally accepted, easy to use formalism that practitioners can use to describe this problem correctly from the very start. And so there's no set of practical methods then also that after describing the problem that you can resort to then go and try to solve automatically the problem that you formulated. And so what is happening in practice, because there are so many effective toolkits to build supervised learning models, is that in practice, people start out building a supervised learning model and then may or may not scratch their heads in future iterations and say, hey, wait a minute, there's something more complicated going on. Right? So in a nutshell, the ambition of this theme in the lab is to change this. Right? So we hope that after 5 years, we have investigated and understood which building blocks exist already that we can use to fill this gap. And if we find that there are white spots remaining in the theory, to try and fill them as good as possible. So both scientifically and in terms of practical applications, a very worthwhile thing to try and achieve. And then you might say, well, why now? And I think in all the disciplines of information retrieval, causality, and reinforcement learning, there has been nice and important advances in the last few years that we can build on. And this is also a segue into Professor Correa's talk, which I think fits very well. To give you a first teaser and also a little bit of a hint of the type of applications that we might be interested in, is let's revisit the credit card story and see how existing word of S recoverability might help. Right? So suppose that we would change the question, the situation a little bit. Suppose this assessment is done by an old algorithm that only relies on input X and not on interviews that humans might have and go unrecorded. Would that change anything? Right? And the answer is yes. Right? And there's a very nice trick that is at least as old as this paper here in 2012 for Berenboim, Elias, and for Berenboim and Pearl, is to write down the graphical model for this problem and explicitly introduce a selection node S. Right? So for those of you in the audience that know of Bayesian networks, we have the input X, output Y, and now S is deterministic or probabilistic, and it looks, when it is 1, the data is entered in our database, and when it is 0, it is omitted, it is not stored. And again, for those of you that know graphical model, in this case, I should say, the selection S now looks only at what is measurable in X. And for those of you that know D-separation, here Y is independent of S given X, which means that we immediately get that this conditional distribution PY given X that we hope to learn to build this classifier is actually the same as P of Y given X and S of X being 1, which means that if we have a data set that is filtered, where we only get, say, the low risk cases, we can still use that to learn the conditional distribution P of Y given X. And for those of you that are less familiar with graphical models and more familiar with supervised learning, let's look at the toy example. Right? So suppose that X is just a scalar, and the ground truth of this default follows a logistic. So it's the blue curve. So if we would sample data, then on the left we would sample more zeros. To the right we would sample more ones. And suppose that our selection process from the old algorithm says that beyond a certain point, this is roughly 1.3 here, all data is discarded from the database. This will not be entered in the database. So that would mean all red points that we could potentially observe will then be filtered out. And the observations then is that where we observe data, for instance, at x equals 0 or around in the bin around it, the ratio of zeros and ones is unbiased and lies exactly at the blue curve. That's why we can learn this relationship despite this bias from filtering. And then the question looking back is, okay, what is then different if they're human judges that have maybe in an interview and discuss things that are not recorded? Then we get an additional variable z, where the default depends on things that are measured in x and in z. And the selection is also based on x and z. And now if we want to build a model of p of y given x, then we can't straightforwardly use this data. And we need to do something more sophisticated potentially, because the selection now is not independent of y given x. And so with that as an example of an existing piece of literature that makes a first step towards this goal of getting a framework where we can describe these problems, and also as a segue to the presentation of Professor Correa that will look at this and other techniques in more detail. Let me finish with also mentioning a little bit that the second theme is natural language processing, multitask learning and transfer learning. Booking works in 43 different languages and dialects. And so natural language processing is important, and building applications for each language independently is very expensive and also very difficult in the low data regime. So this is a topic we might discuss at another point. Before taking any questions and handing over to Correa, let me also highlight the great team of people that we're super happy to be working with. And we hope throughout the years to keep you up to date with the progress that we make. If there are any questions or comments, I'd love to try and answer them.
Yeah, so thanks a lot, Onno. For those of you who have questions, you can raise your hand by clicking some button, and then I may give you the floor. There's also the question and the Q&A tool that you can also use to type your questions during a presentation. There we will, yeah, so that's another way to pose questions. This is also for the talk that we for the presentation of Professor Correa that we will hear in a moment. You can post your questions in the Q&A and we'll take note of them, or you can raise your hand, although I'm not sure if I will see it if you raise your hand in time, but I'll try to monitor the list. So I see no questions. So let's continue then with the presentation by Professor Juan Correa. Professor Correa is assistant professor at the Universidad Autónoma. This is hard to pronounce. Universidad Autónoma de Manizales, Colombia. He got his PhD recently from the computer science department at Columbia University, was advised by Elias Breinborn, and Correa's research has been about the identification of causal and counterfactual quantities by combining different heterogeneous data sets and making use of graphical causal models. And Professor Correa has developed several algorithms and graphical conditions to cope with challenges like selection bias that we already heard about in Onno's presentation, and also to deal with data coming from different experimental conditions or from different domains, and all of this in a non-parametric setting. We will have a few breaks during the talk for questions if necessary. And after the presentation, we will also have room for some Q&A. So without further ado, I would like to give the floor to Professor Correa to speak about generalization of causal and statistical quantities under transportability and selection bias.
Thank you for the introduction, Joris. So let me get started and use my time wisely. So I need to say that this is work that I developed during my years as a PhD student at the Causal AI Lab at Columbia University. So credit of all of this is also shared with my advisor and co-author, Elias Barenboim. Maybe for some of the results I will discuss here and maybe some others I will mention, you could find many papers in the lab's website, which is listed here. So let me start with a brief introduction. So these problems are about causal information. Causal information could come in many forms, but in terms of quantities, we distinguish like three kinds of quantities based on something called the ladder of causation of Pearl's causal hierarchy, like association, causal effects, and counterfactuals. But here we will mostly talk about causal effects, but because they help us taking decisions and so on. And this is an important piece to build AI systems and applications in general to support scientific discovery and so on. So what we like to do is to discuss how to infer causal and statistical quantities, meaning associations like the probability of Y given that I observe X, and causal effects like the probability of Y given that I do X, that I make an intervention in the system. And we would like to infer these kind of quantities from a combination of heterogeneous data that could come from different domains, meaning different populations, or if we are talking biology, it could be different species. And we could also have another dimension, which is different experimental conditions. Some data may have been captured using a survey, so it's observational data. Some other data could come from a randomized clinical trial or some kind of controlled experiment where some variables have been controlled for. So we could have experiments, observations, and also we could have situations where the samples are not randomly obtained from the population. So there is a different proportion of what we see in our data set compared to the general population. Then the question we'd like to ask is how to systematically and at least in principle non-parametrically evaluate this kind of distributions, interventions, and associations based on this kind of heterogeneous data set. So I would first formulate some data fusion tasks, and I will talk in a second about what data fusion means. But basically it comes from this concept of having heterogeneous data sets and combining them in order to infer some target quantity. So in this wording, I'll phrase a task called identification. Hopefully, some of you here are familiar with what causal effect and identification of causal effects mean. And I will talk about three specific tasks. One is called soft transportability from observations and experiments. Another one is called statistical transportability across domains. And another one is called recovering causal effects from selection bias. Then I'll summarize some of the results that we have been able to get in our research from this perspective in these tasks. And I'll just conclude. So in order to make this analysis formal and non-parametric, we use structural causal models. I will briefly describe these for those who may not be familiar. So a structural causal model is a tuple of 4 elements. We have the variables that we observe, or endogenous variables, what we actually get to see, unobserved variables or latent variables, which are factors that are present in the data generating process, but we do not get to see. And we are assuming here that each one of the variables that we do observe take their value given some mechanism that in principle is hidden to us, but is a mechanism which is a function of some subset of the observables that we call the parents here, and some subset of the unobserved variables. And then over these latent variables, there is some unknown distribution P of U. Even though we usually don't assume that we observe this kind of model, what we do assume is that there is some data generating process behind the data that can be modeled in this way. This is not the only way to model it, and has some limitations, like when we think of feedback, cyclic relationships, but in principle is a good starting point. So this kind of tuple could be, we have three observed variables, z, x, y, and then we can define functions here to the right that combine both observed variables, like the function for x here is an XOR taken from two unobservables named ux, uxz, and an observable z in this case, which we will call a parent of x. And then we define a distribution over the u's in this case. So this is just to instantiate this kind of tuple. But more interestingly, what we usually do assume to know in this analysis, and then we can talk later about how to get this in practice, but every SEM induces some graph that we will call a causal diagram. And this causal diagram has the following elements. There is one vertex for every observable. There is an edge from one observable to another if the one at the head is a function, or the function that gives the value of the variable of the head takes into account the variable at the tail of the edge. And we also have bidirected arrows between two variables if both of them depend on the same unobserved variable, or the unobserved variables they depend on are not jointly independent. So there is some relationship that we don't see between the variables. In the example before we had these functions, and we can translate that into this diagram. Again, we have three observables, therefore we have three nodes. Here z is in the function for x, so there is an arrow from z to x. And x and z appear in the function for y, so we have arrows from x and z to y. And finally, both z and x take into account this unobserved variable u sub x z. So we have this bidirected because they share some latent confounding. So using those concepts, we would like to think of a causal inference engine. This is a concept that Julia Pearl has talked about in his books and so on. And it's basically this idea where we have some quantity that we want to know, a query. We'll usually express these as a probability distribution, can be a conditional probability distribution or a causal probability distribution. We have some input data. In the classical setting, we just have observations, and we have some causal assumptions in the form of this kind of causal diagram. Then this engine, we would like to see if, given this query, the input data and the assumptions, if there exists a function of the data that we have such that that is equal to Q for every data generating process that satisfies the assumptions that we have. So here the assumptions are constraining the space of possible data generating processes. And we would like to know if there is a single function that is equal to the causal effect or the query of interest given the data that we have. So the answer could be yes, then we have the function f, and the answer could be fail in the case where the causal assumptions are not enough, or the data that is available is not enough to pinpoint this specific function. So we would discuss in the context of this inference engine a causal inference task, and we'll say that a causal inference task has three components. It has a query Q, a set of input data P, and a set of assumptions G. And then we will say that the signature of the task is a tuple of these three elements. What is it that we want to know? What is the data that is available? And what are the assumptions that we can make about the data generating process? In that sense, the identification problem, the most common one in causal inference, could be stated as follows. So in many fields, one of the goals is to predict what would be the reaction of an outcome Y if we take a certain action X. This is usually written as P of Y given to X to this do operator is saying that we are not just simply observing X, but we are making a change. We are intervening, taking a decision, implementing a policy, or so on. And then to answer this kind of question, we have a distribution, a joint distribution over the variables that we just observed. So when we want to know this kind of effect from this kind of observational distribution, we will say that is identification from observational data, or OBS ID. This is related to the potential outcome framework. There are graphical conditions to solve this problem, like the do calculus or the backdoor criterion, since many years, 90s, 91, 93, 95. And there are also algorithms that are sufficient and necessary to solve this task non-parametrically. And we can write the signature this way. The query is some causal effect, some P of y given to x. The data here is just an observational distribution, and the graph is a causal diagram. So in this case, we can see that the query basically refers to an alternate reality. We have some situation, and then we are making a change. Let's say that before x was a function of z, but since we are changing or fixing the value of x, then it is not a function of z anymore. In this example, we have that age may affect how much exercise people do and the condition of their heart. But then if we are changing or forcing people to exercise regarding of the age, we put them on a regime, then we are severing this relationship between age and exercise and making a change. And we want to say something about the system after this change has been made. This is kind of the meaning of the intervention here. So there are other tasks similar to this. So this is the one that I just described, but we can have variations. Instead of just having an observational distribution as input, we could think of experiments. Let's say that we have a randomized clinical trial where some treatment was evaluated, but we want to say something about an additional treatment or a different treatment on a different variable, or we are intervening in a different part of the process. So one variation is called the GID problem, where we have observations and we also have interventions, a given set of interventions. So depending on what available data we have, we input that to the problem. Still, we have a causal diagram, and we have, again, algorithms and conditions to figure out this problem non-parametrically in this setting. There is also another variation called GTR, where we are now thinking about several populations. So we not only have data from one population, but we may have several populations. And now we have a super index here in the distributions, this I. So we could have, again, experiments and observations from different domains. You can think of this as observing some customer behavior in different states, like in California and New York and Indiana and so on, and combining those data sets. In one place, we could have performed an experiment, like an IB testing situation, for instance, in one of the states, and in the other state, we just simply got the logs of the application to get the data. So in one case, we're observing, one case we have experiments, but the problem here is about how do we combine that to assess a causal effect. Then I will talk about the first task specific to my research that is similar to the one I just described, but has a twist. So the idea is to generalize policies, meaning we are not just fixing a value as the do intervention I described before, like we are making everybody exercise or nobody exercise, but we are thinking about a policy that could be conditional, stochastic. So the idea is to figure out the effect of a new intervention or policy. And this is a common task in many sciences and applications. Usually controlled experimentation is considered like the gold standard to get these kind of effects, but sometimes even if you can perform the experiment, which is already hard in some settings, the experiment does not necessarily generalize to other domains beyond the population that you got for the experiment. And there are many empirical sciences where there are tasks where we have this kind of, or that we can instantiate in this kind of frame. In the literature, this is called transportability theory, which is about how do I use data from different domains to say something about a particular domain of interest in terms of usually causal effects. So we specifically look at the generalization of policies from a collection of experimental data. Then let's consider an example. I'll quickly go over it. So don't pay too much attention about the details, but the general situation. So let's say that we have that in some city that we will call Pi Star, we want to increase the number of homeowners, and then we would like to implement a policy where we relax the credit history requirements that some banks impose so that people can borrow more money and then purchase more houses in a certain area of the city that we want to develop. So if the situation is like this, here again, there is a more complex causal diagram, but here what we would like to know is if we create a policy that affects X, which is the percentage that people is allowed to borrow, usually that is affected by things like what is the property they want to buy and their credit history, and this at the end gives rise to how much they really borrow, and at the end we would like people to pay. So a good indicator here, or the outcome, would be if people is paying promptly their loan. So with this kind of diagram, we can use the theory I described before to get that this is not identifiable from observational data. If I just go to city by star and observe the current behavior about credit history, loans, percentages, payment, that won't be enough to say or to predict the effect of changing the way that this X behaves. That in this case, we are ruling out some relationships. So we are making X a function of the R, in the sense that we are reducing the increasing the percentage people can borrow as long as they are buying from a certain area of the city. So now credit history, don't look at that. Other hidden confounders, don't look at them. We are just going to look at the property. If it is in this area, we will allow this percentage, and the city is going to back up those loaners if that is the case. So that is the kind of policy we're thinking about. But since we cannot predict this intervention just from observation, then we will consider other sources of data that could come from different domains and could have different experimental conditions. In particular, here in this diagram, I used an extra element, which is this square node annotated with sigma x. I'm using sigma here to represent a policy, a change of the way a variable is behaving in the system. And this square node is pointing to the variable that is being changed, and this arrow in yellow is showing what changed from the original system. So as I said before, these influences here that are in a lighter color, they have disappeared, and now the X depends on R, or the policy that we apply depends on R. So the first thing we can try to do is to use different data from different domains. So let's say that there is another city we'll call Pi1, and Pi1 is different in the sense that the credit history of the average lender is better. They tend to pay their loans more promptly, let's say. And there is another city, Pi2, where the properties tend to be cheaper. So this is one of the properties of this is one of the characteristics of the property. So there is a change in R. So here I am adding another element to the diagram. These green square nodes annotated with the name of a domain or a population, and they point to the variables where there are changes. So as I said before, in city Pi1, the difference is in the credit history. So we have a square node pointing to credit history annotated with Pi1. For the city Pi2, there is a difference in the characteristics of the properties. So we have a square node we annotated with Pi2 pointing to R. Basically, we want to capture the differences between the data generating processes in different populations. And for now, we are assuming that we can get to know this. An interesting problem is, how do we learn this kind of differences if we just have data and maybe the causal diagram? So here we are considering data from two other domains, and we are saying how they differ. Again, these square nodes are indicators that there is a change in the mechanism or the distribution for some variables between domains. The other dimension is different experimental conditions. So let's say that in city Pi1, it is not that we just observe or it was just the observational data, but someone ran a study. They used a policy where the amount that was allocated was based on the percentage and the features of the property given a fixed formula. So they did perform an intervention, they ran an experiment, they changed the way that it naturally the loan process naturally went, but we want to reuse that study. That is not the intervention that we want to make. We want to relax the percentage they can get, not to fix the amount they can borrow based on something else, but still we can leverage this data to say something about our query. In CityPy2, let's say that they simply randomized credit history. So they took a bunch of applications to credits, and in order to check how much did the credit history affected the process, they just replaced the credit history with different types of credit history at random, and then they evaluated, okay, let's see how much was the influence now that we completely randomized and controlled for credit history. And again, it's not the intervention that we want to say something about, but still we can leverage the data there to say something. So here, coming back a little to the signature of the problem, here the query is a policy. So I'm not, instead of saying y given to x here, I'm not saying do, because I'm not fixing the value of x. I'm using this notation where I specify a policy. So the sigma x is the policy that I described before, that whenever the property is being bought in a certain area of the city, we will increase the percentage. And this star is marking that I want to say something about the domain star, CityPy star in this case. Here I have three distributions in the input. I have observations in CityPy star. I have one starting CityPy1, one starting CityPy2. And I have these different diagrams. And basically I have the observational diagram, the diagram that represents the system after I make the intervention, the diagram that shows me the differences, the diagram that represents one of the cities with their intervention, and the diagram that represents the other city with its intervention. And I can just take all of these and summarize it in a type of diagram called the selection diagram. That would look like this. So the interventional part I can always derive from here, but here I'm capturing the structure and the differences between domains. So if you look at some of our results, if you are interested, there are sufficient and necessary graphical conditions and algorithms for solving this problem. So again, the input is these elements. What is your query? What is the data that you have available? So you can list the kind of studies that you have, or the interventions, the experiments that you have available, and then your graph. And this algorithm will give you a function, if it exists, that is equal to this query in terms of these distributions, or will say no in the case where there are not sufficient assumptions. Let me ask if, at this point, if there is any question. If there are no questions at this point.
Maybe
yeah.
You can elaborate a little bit on what you mean with necessary and sufficient conditions, and what type of conclusions you would draw in this particular example.
So what I mean by sufficient is that whenever the algorithm gives you a function, it is guaranteed that it is being correct. It's not approximate. If, at least in the limit, if you have enough samples, when you compute this function of the input data, you will get the query. Of course, as long as the assumptions in the diagram are correct, but it's giving you that guarantee. And necessary means that whenever the algorithm says no, we can always come up with two different data generating processes that have exactly this causal structure that gives you exactly the same distributions that you are observing, but they give you different results for the query. So it's basically a proof that you cannot be certain what is the data generating model that you have, and that different generating models could give you exactly the same diagram and input, but still have different values for the query. Therefore, we cannot say something without further assumptions. That's what it means in terms of sufficiency and necessity. Now, in terms of what we can say about this particular example, I think I didn't write expression here. Let me see, maybe, let me see. So I think it was this example. Here, for example, the function looks like this. So the query is equal to this function. And if you look at the terms in the function, we have the distribution P1 with this sigma z, which is the study that was performed in CDPy1. And we also have terms related to CDPy2, which have these randomized study and credit history. And we also have some terms. This term is related to the last term here, P star is an observation on the target domain. So the distribution of the characteristics of the properties in this target domain. And we have this other term that is related to the policy, which is exactly what we said, how X is defined given the value of R based on the policy. So we have 4 different kinds of terms here, one coming from one population, Pi1, one coming from, others coming from Pi2, others coming from Pi star, and other that is defined by our intervention. So this is the kind of result that we will get, an estimator for the target query based on the input data that we have. I hope that helps clarifying it a bit.
Yep, thanks.
Okay, so let me quickly describe another task in this sense. So another task more related to machine learning is how to generalize, let's say, a predictor from one domain to another. So usually the problem here is that there is a change in the underlying distribution that we are talking about. So we train the data in some distribution, but we are actually going to deploy the system in a different distribution. And these have different names like statistical transportability in the causality literature, data set shift, transfer learning, domain adaptation, out of distribution prediction, and so on. So here, the way we will define the task is that we have 2 domains, the domain where we train and the domain where we want to say something about, but we are not specifically talking about what is the best predictor, but for now we will think about a distribution in the target domain, like a distribution of the form y given x. And we would like to say something about that distribution using data collected in a different domain, let's say the training domain, for instance, and maybe a little bit of data in the target domain. So let's say that we have some website where we have, based on the age of the user, we present different types of advertisement, and then we check if the person bought or not the product of the advertisement. Then we have a different website, maybe a different country or a different kind of product of website where we assume that the way we are picking the advertisement is the same, that the buying behavior in general is the same, but the users in average have different range of ages. Then we would like to use the data that we got in the current website to say something about the new website in terms of predicting how much they will buy based on the type of advertisement that we give. So on one side, we have the joint distribution of these variables, our data set in the target, in the source domain or training domain. I want to say something about this distribution in the target domain, y given x star in the target domain. So in this case, we can rewrite this quantity of interest. I'll just give you a quick example. I'm just opening the expression and using some probability axioms here. But the important point is that after writing the expression like this, based on this diagram, using this separation, if you're familiar with that, and using this square node that again is representing the differences, we can look at these distributions and know that they are the same as in the source domain. That is to say, the distribution of y given x and w is invariant to the changes because this square node cannot change the distribution of y once we control x and w, which is what we have here. So I can rewrite this expression or remove, quote unquote, the stars from these terms, and I am left with just the star in the term for w. So under the assumptions implied by the diagram, I'm running out of time now. Under the assumptions in the diagram, we can estimate this quantity in the target domain just by measuring these variables in the source domain, our training, and just measuring in the target domain the distribution of w. So here there is a mix. We are writing our target quantity in terms of something that comes from the source domain and something that comes from the target domain. So we could have, we only need to measure w in the target to estimate our target quantity. And this is nice because we are assuming that we have more data in the training setting and less data in the deployment kind of setting. So here again, if we write in terms of signature, we have again a query, we have input data, and we have a diagram. That in this case is a selection diagram. And again, we have this tuple of 3 elements. And in this paper, we have again sufficient and necessary conditions and algorithms for solving this problem non-parametrically. That's to say, you can check whether there is a function of the available data that is equal to your target query given the assumptions in the diagram. Just to give you a sense of how this problem is not trivial, we can see a table here where the rows are different causal structures. They are very simple causal structures, just like a chain, a fork, a collider. And in the columns, we have different positions where the differences can be between source and target domain. And below each figure, we have whether you need, what kind of measurements you need in the target domain. What variables do you need to get in that target domain in order to follow this process and get a formula. So you can see that across different structures and across different positions of the square node, the result changes. Even for the chain, we have, if the square node is in X, we don't need data in target domain, meaning the training data set is enough. If the differences are in this variable in the middle, then we will have to measure Z and X, not Y, but Z and X in the target domain. And if the differences are on Y, then we'll need to measure Y and Z in the target domain. And we can see this pattern repeating in other places. So this is saying that both the structure and where the differences are is important for this problem. Just to finish quickly, the other task, and I will leverage the fact that at the beginning we heard a little bit about this, is recovering from causal effects from selection bias. So this is where we model explicitly the selection mechanism. That is a variable that is equal to 1 whenever we observe the sample and 0 whenever we do not observe them. And we explicitly put that in our diagram as a note. And here the idea would be, if we observe a distribution that is biased, there is selection there, how can we say something about a non-biased quantity? So something that applies to the whole population. In this particular example, we are saying that people that exercise more is more fed, and we are serving people that tend to be on the feeder side. So we are seeing more samples in our data set of people who has better fitness, therefore they exercise more, and we would like to see the effect of exercise on cholesterol. So we have a different proportion in our sample than the whole population. Again, the task can be solved. Let me skip this because I will have time to do it, but again, here the signature of the task is a little different. We can consider data that is selected, and we can consider also some data that we know is not selected, like census data, for instance, right? Like you have a particular study where the samples are not taken at random, but we do have some examples from the general population, census data, and so on. Again, we have a diagram, but this time it is augmented with a S node. And we again have some sufficient and necessary graphical conditions for the case where you just have some selection bias data. And when you augment that with data that is not biased in that sense, then we have a sufficient algorithm. And this is also in this paper. Then let me conclude. And in case you have more questions about this, I can use the time to go back to it. So there are several...
so you have plenty of time, right? You have still about 10 minutes or so to finish your talk.
I have 10?
If you want.
Okay, I thought it was 35, so I thought I already went over. Okay.
No, you have until, well, 10 more minutes, say, if you want to go in more details.
Okay.
Meanwhile, also more questions have appeared. So you can decide in which order you want to proceed.
Okay, let me see. Okay, then let me go over the selection bias a little bit more, taking into account some of the questions here. Let me see. Okay, so let me address some questions here. So about one question says, did you have the chance to compare results of an analysis using the model that combines data from different domains with the results with a well generalizable experiment? I don't have a particular experiment like that, but usually in the analysis, we are thinking about situations where you cannot get and you cannot make the analysis any other way. Like you cannot perform the experiment in the target domain, but maybe you can do it in another domain, and then you can try to leverage that data to use it in another domain. But specifically, I cannot point out to a particular comparison like that. But if you want to take it offline, I think I have seen some papers that may have done something like this in particular settings that I could point out. For the query, the solution for the query of the first task, is there an automatic system? Yes, for some of these tasks, there is already some implementation that we have in the lab, in the Causal AI lab at Columbia. And if you're interested, I can get you access to a system that we have called Fusion, where we have implemented some of these algorithms. So basically you draw the graph, give the input, and then you'll get back the function if there exists one, or kind of a witness that there is no function in the non-parametric setting. And for your question about the selection node, then let me go over this slowly and I'll highlight that. So again, here we are assuming that the S node is representing the mechanism by which we include a sample in the study. So it is always a sync node, because we are assuming, or we are not considering a situation where after you decide if the sample is in the study or not, something else happens, meaning the variables Z, like the age, X, the amount of exercise people do, their cholesterol level, their fitness, it is not affected in any way by whether they participate in the study or not, or whether they are surveyed or not. So in most of these cases, or at least in all of these, all the cases in this setting, S is always a sync node. There is nothing that S points to, because that would mean that being included in the study is changing something about the sample. But here, it is just representing a matter of whether we observe the sample. So all values that are observed are already fixed before we get to see or not see the sample. So in principle, there could be only nodes pointing to the S as a sampling mechanism, and not the other way around. So again, here we have a study where we want to say something about the effect of exercise on cholesterol, and we know that age affects both things, and we know that depending on how much people exercises, their fitness level is different. And then if we go to a gym or any other place where the fitness level of people in average tends to be different to the fitness level of people in the general population, then we would have bias in our sample. The proportion is different, and then the fitness is what is changing the likelihood of being included in the sample. So one way to...
So
yes.
Juan, there was the question by Dimo. He raised his hand, so I guess he wants to follow up on his question.
Go ahead, please.
Yeah, thanks. There's a question about if you were able to compare results with a generalized experiment. I understand, obviously, the value of this whole analysis is exactly when you cannot have the experiment, but I'm curious if there has been some sort of validation of the whole methodology and algorithms that you've created here.
I mean, beyond synthetic data, I cannot, I don't have any validation like what you're asking. But again, if you want to take it offline, I have seen papers where they use transportability, which it would be the task in this case, and compared with different settings. In particular, I remember one study where they took data from several studies, similar studies in different populations, and then did a transportability kind of task. So they combined the data sets to set something about a new domain, And afterwards, they run a similar experiment in the new domain, and then they compare how this generalization was, how much different it was from the actual experiment in that setting. But I don't remember exactly the reference from the top of my mind. So if you are interested in that, I can point you to that if you.
Just in general sentiment, do you remember if it was positive, like if it was conclusive in a sense, or positive even, or?
Yeah, I remember the prediction was very close, like the error was not too high.
I wouldn't expect to catch exactly the same number, but I guess validation is always.
But it was close.
Yeah, nice to hear. Thanks.
So one way that we could try to recover, anyway, that is the name that we give to this kind of task, which is recovering causal effects, or also probabilistic like observational distributions, recovering them from selection bias. So we have a situation where there is sampling selection bias and we want to recover some quantity out of it. So one way to do that is with adjustment. If you are familiar maybe with the backdoor criterion or the adjustment formula, we generalized this formula and it'll look like this. So the point here is that we want to say something about the causal effect of that X has on Y. So what happens with Y if I change the value of X, if I fix it to some value? And here to the right, we have three factors. So the first factor is a conditional distribution. So this comes from observations, and we have the S equal to 1 here, meaning this is an observation that comes from this sample selection bias distribution. Then we have a second term where we have some part of a set Z. So there is a set Z, and we are removing some part of Z here and conditioning on that. That is also selection biased. And there is a part of Z that comes, that has this superscript T. So the idea is the following. We have a treatment X, something that we want to change, intervene on. There is some outcome Y, and there is a set of covariates Z. So this set of covariates could be things like age, language, race, and any other variable that is not the treatment and the outcome that we could also observe in the study. And here we talk about an adjustment pair. So an adjustment pair is a pair Z and C superscript T, where the second one is a subset of the first one. And we say that an adjustment pair, that this pair is admissible if the causal effect is equal to this kind of formula. So if you take a look, this is our reweighting. We are summing over the possible values of Z, and we are reweighting this conditional distribution Y given X and Z that is biased here. And we are reweighting it by two pieces. One piece is also biased in terms of some set of covariates, and one piece is not biased. So again, this is biased data. This is a little bit of external data. And we say that this adjustment pair is basically describing a mapping between the data that we have available and the target causal effect. So there is a criterion that we can apply. If you have the diagram and you have the variables, you can apply the criterion to check if some set Z is admissible for that. So I will not parse this right now, and it's not that important for the discussion, but the point is that there is a criterion that I can look into the graph, let's say this graph, and we would like to find a pair Z, ZT that is admissible, meaning that we can write this formula when we are reweighting Z and make it equal to the causal effect of interest. So if we look at the set Z1, C2, and C3, so this variable Z1, this variable C2, this variable C3, we can verify the conditions there, and if the conditions are satisfied, then we instantiate the expression. So in this particular case, the effect of X on Y, meaning Y given to X, is equal to summing over these three variables and then getting these conditional distributions. Again, one part of it comes from a sample, from a selection bias distribution, and one part of it comes from a non-biased distribution. And this is a complete criterion, meaning whenever the criterion says that some pair Z and CT is admissible, then this formula holds for any model that satisfies the assumptions in this diagram. If the criteria says no, it means that, again, you can find two different models that satisfy the same diagram, that give you the same data, but this effect is not equal to this formula. So they won't match. You won't be able to use these to uniquely characterize the effect of interest. There is also a systematic way to get all the possible pairs. So this criterion is just given a particular pair, it tells me yes or no, it is admissible or no. This formula holds or this formula doesn't hold. Now a good question is, how do I get the possible pairs that could give me this situation? And for that, we consider as a particular class of algorithms. If you like computation, this is interesting. So the number of pairs that you could get could be an exponential number. So just listing the possibilities could be exponential in time. So there is one class of algorithms called the polynomial delay kind of algorithm. And the meaning of that is that the time that after you start the algorithm, the time that it takes to get your first result is polynomial. And after the first result, the time that it takes to get the next result is polynomial. What being polynomial means here is that it won't take too much time to get you one result and get you the next one and get you the next one, or say there are no more results. But then again, you can just list the sets. That is for this particular kind of formula, right? When we say adjustment, what we mean is that the formula has this form. But there are situations where you can still get the effect using a formula that doesn't have this form. And the particular thing about this form is that it is usually easier to estimate. We understand it better. There are some techniques to estimate this kind of formula. But then we have some situation to, in general, identify this kind of thing. So this is a slightly not so complicated model where there is no adjustment that will work. But still, we can find the effect using a different kind of mapping. This looks like a more complicated formula, but it's definitely not adjustment. It's like a combination of two adjustments. But still, we can think about this problem in general to get any kind of formula, and we have an algorithm to solve that. So again, we can write this as a task. Our query could be a causal effect. Our input, this bias distribution, some subset of the variables that we measure without bias. And again, there are also algorithms to solve this more generally, if you are interested. So just to summarize here, I described some tasks, and the last one here I didn't describe, but let me parse that one just to familiarize you with the table. So again, we have a query, we have data, we have the graph, and this last task here is called generalizing experimental findings. In this task, we have the target is a causal effect in some domain pi star, and the input is a randomized trial. There is a do-X here, but the trial is also selection biased. So there is sampling selection bias in the study. Like there was some inclusion criteria in the study that made it so there was bias, but still it was randomized. And there could be differences between the population that we have in the study and the general population. So we also have some data in the pi star. So the study is run like in a particular town or for a particular group of people, and then we want to generalize whatever we found there to the general population or a different town, and there is selection bias involved. So there is also some adjustment criterion that you can use to solve this kind of thing. And then we can see different types of tasks, but all of the same flavor, non-parametric, and to find conditions and algorithms. And in general, the algorithm that solves this kind of thing that you can, and that there's most of them, they have implementations, they are efficient in terms that they do not take too much time. So to conclude, there are several tasks in the context of data fusion problems, like combining different data sets that can be solved non-parametrically with the help of a causal diagram or a selection diagram. This setting can accommodate different problems in empirical sciences that involve heterogeneous data sets and also causal and statistical quantities like conditional distributions or causal effects. And there are efficient algorithms that are sufficient and necessary to solve this task non-parametrically. And If you are familiar with do calculus, for instance, and covariate adjustment that I mentioned a little bit, there are generalizations in these tasks of those tools to solve this kind of problem. Just to briefly mention, for most of these tasks, I am assuming that there is a selection diagram involved. One good open question is, how do we learn this kind of selection diagram from data if we don't know it? So that we can lower the load in terms of the assumption that we need to make. So this is what I wanted to say. So I guess it's again the time for questions.
So thanks a lot, Juan, for this great talk. And indeed, if there are further questions, and now is your chance. So one thing I was wondering about is if you have different ways. So your causal inference engine, you have it output a single formula, but sometimes it might output many different possible formulas that all identify the query or the distribution you're after. So can you say anything about how to choose, whether some answers might be better than others, perhaps in terms of the statistics of the estimators involved, if you make use of those formulas? Is there anything you can say in general?
Okay, so yeah, that's an interesting question in the sense that here by default, the engine will give you one answer, but that's not necessarily the only possible function, as you said. And different functions could have different properties. For example, less variance or be easier to estimate. So I don't have work on that personally much, but I have seen work in progress where the idea is to find, in principle, to list different expressions, possibly all of the expressions that could be valid functions of the input data that are equal to the output. And specifically for adjustment, for covariate adjustment, I have seen some work on checking whether one adjustment is better than the other. And it usually goes on looking at the variance that they produce. Since they are all adjustments, then the estimation is similar. Well, unless you have less or more covariance, then you reduce a little bit the complexity of estimating it. But I think there is not a definite answer there, but for sure is an interesting problem to think about. One way to kind of get different formulas could be if you have like an automatic way to get this, like if you use the algorithm, you can try to hide some variables. Like in the model, we are making a distinction between observed variables and unobserved variables. If at some point you want to get a formula that does not include a particular variable, then you can quote unquote hide it. Think about it as a latent variable. Then think about what would be the diagram if that variable was latent, and run the process again. And it could find a function that does not use that variable and gives you some kind of expression. And hiding different variables, you could get different kinds of expression. And this could also be relevant for how costly it is to measure something. Like, let's say that I'm running a study, and for the covariates, I'm thinking about the effect of a drug on a particular disease. And I have two formulas. One formula asks me to measure a genetic condition on the patient, and the other asks me to record how many headaches the person got in a week during the study, in average, for instance. So if I have two formulas, in one case I have to measure some genetic condition, in the other case I just have to measure the frequency of headaches, then one formula will be cheaper than the other because I don't need to run a bunch of genetic tests then. So it could be relevant in that sense. So I just try to say what I know about it, but I hope that clarifies it a little bit, but I don't have a definitive answer.
Yes, thanks. That's quite helpful. So I think it's in general, of course, with all these different types of different, well, versions of transportability and S recoverability problems, there might also be all kinds of different versions of finding better or optimal formulas, I guess. So this could also be a huge research field on its own, perhaps. Are there any other questions? Philip, perhaps you have, well, we are almost at 4:30, so there's not much more time for questions, but so this might be the last question then.
Yeah, so you have
how long it is.
as general assumption that you know the causal graph and that you have your selection bias data. And additionally, you can assume that you have some census data or some external data. Is there a next logical, not too restrictive assumption which you can use to recover from selection bias or solve transportability questions?
Okay, yeah, so in these tasks, whenever I consider like biased data and unbiased data, like in this case, this T could be the empty set, meaning even if you have a situation where there is no census data or anything like that, you can still run the analysis. Of course, the range of instances where you will get a negative result will increase because this external data is helping, but it doesn't mean that in the analysis you cannot consider not having external data or not having data in the target domain. You could consider a situation where you only have data in the source domain and try to run the analysis. That is in terms of the analysis. Now, in terms of how do you, if you have some data, have some assumptions, but the answer is no, you cannot get a solution, where do you go from there? So one way in terms of practical, in a practical situation could be to measure more data. If that is not an option, and if you want to make more assumptions to help the process, then you could go to parametric assumptions, right? Here, non-parametric, I am assuming that there is a data generating process, but I'm not saying if it is linear, if it is Gaussian, I'm not saying anything about the distribution or the form of the functions. So one way to move forward could be to make some assumptions in that sense, but still getting the theory and general conditions for particular parametric assumptions is still an open problem, but it can also be taught in a base-to-base cases.
Okay, so I think we're running out of time. So thanks a lot again to Professor Correa for a great presentation. The next installment of this webinar series will be on March 31st, where Nikos Vlasis will speak on reinforcement learning. But this will be announced. So I hope to see you all again, and thank you for your presence today.
Thank you.
Thank you.